Bismillahirrahmanirrahim. Assalamu alaikum, students. Last time we discussed the Doppler effect in sound. Today we are going to discuss the Doppler effect in light. So our topic is, let me use this color, the relativistic Doppler effect. Relativistic Doppler effect. And I will write in the bracket Doppler effect in light. Remember, in the last lectures, we discussed Doppler effect in sound, and we used the general formula nu is equal to nu naught times V plus minus VO over V minus plus Vs. Nu is apparent frequency, nu naught is actual frequency or real frequency. V is the velocity of the sound wave in the medium. V naught is the velocity of the observer or listener. Vs is the velocity of the source, and the signs we have to take appropriately depending on the situation of the relative motion between source and observer. We've already done a problem related to this formula. We use it all the cases. And remember here, the velocities are expressed relative to a reference frame at rest in the medium in which the sound wave travels. As we already discussed, there is a difference between the Doppler effect in light and Doppler effect in sound. What is the difference? I will write first, then we will move forward. In the case of sound, I've already told you, but I'm just refreshing you. In the case of sound, the motion of the source with respect to the medium of propagation can be distinguished from the motion of the observer with respect to the medium. Light waves are analyzed differently because they require no medium of propagation. This is very important, that's why I'm writing it. They require no medium of propagation and no method exists for distinguishing the motion of a light source from the motion of the observer. Need to remember it. I repeat, in the case of sound, the motion of the source with respect to the medium of propagation can be distinguished from the motion of the observer with respect to the medium. Light waves are analyzed differently. Why so? Because they require no medium of propagation and no method exists for distinguishing the motion of a light source from the motion of the observer. Let us now discuss the formulas related to relativistic Doppler effect. I will draw a figure. Let this be my observer O, and I emit figure 1. And this be my source. And the source be moving with velocity u. And you can use another color. Let this be angle theta. Will explain the figure. So consider a source that emits electromagnetic radiation with a frequency nu naught as measured by an observer who is at rest with respect to the source. So we are considering a source that emits electromagnetic radiation with a frequency nu naught, but as measured by an observer who is at rest with respect to the source. This nu naught is sometimes called proper frequency. Remember the idea of proper length, proper time, and your proper frequency. Now suppose this same source is in motion. With respect to another observer. To another observer. Who measures the frequency nu of the radiation received from the source. Now, with the angle theta, with the angle theta and velocity u of the source as defined in figure 1, the frequency nu as measured by observer O is given by the Doppler equation. Write it, then I will explain. Nu is equal to nu naught times square root of 1 minus u square by c square over 1 minus u by c cos theta. Let me encircle it and explain it and name it, I think, equation 2. And let this be my equation 1, Doppler effect for sound. Now, so in the figure 1, I have a source moving at speed u, and there is an observer O who is receiving the light electromagnetic radiation emitted by this source at an angle theta as shown in this figure. Now, if the observer is at rest relative to the source, that means if the observer is moving with the source, then the frequency observed is nu naught, proper frequency. But if the same source is moving as shown in the figure and this observer receives the electromagnetic radiation of this source at this angle theta, then the frequency observed by the observer shown in the figure 1 is given by this equation, right? You can see this equation is different from equation 1. Reason, as we have already said it or discussed it, that sound is different from light. What is new? New is the frequency observed by the observer shown in figure 1. Nu naught is the frequency observed by the observer who is at rest relative to the source. U is the velocity and theta is the angle shown in the figure. So this equation gives us, see the speed of light, you know that. This equation gives us the relationship between nu and nu naught in case of the situation shown in figure 1. Now, if, let me discuss the cases now. If this source and observer are moving toward each other, theta is 0, and we have, you can see in the figure, if the source and observer are moving towards each other, this theta will be 0. Either observer is here or source is here. Theta will become 0. And when you put theta equal to 0 in this equation, cos 0 is 1, you will get this expression. Nu equal to nu naught under root C plus U over C minus U. Let me encircle it. And name it equation 3. I have simply substituted theta equal to 0 in equation 2. And this is valid when source and observer are moving toward each other. So nu is nu naught times square root of C plus U over C minus U. You can see nu is greater than nu naught from equation 3. Nu is greater than nu naught. So frequency observed is greater than the frequency observed by the observer who is moving with source or who is at rest relative to the source. You can get this from equation 2 when you put theta equals 0. It may appear different, but it is not different. You can write this 1 minus u by c. Then you can write using the formula a square minus b square. You can use a square minus b square is equal to a plus b into a minus b. When you use that in the numerator, then you will get this form. Now, if the source and observer if the source and observer are moving away from each other, theta is 180 degree, and we have nu is equal to nu naught square root of c minus u over c plus u. Let me name it as equation 4. First check it from the figure. When theta is 180 degree, source and observer are moving away from each other. If theta is 180 degree, source is here, moving away from the observer. So in that case, nu will be less than nu naught. So how can you obtain that? You have to put theta equal to 180 degree. Cos 180 is minus 1. It will become here 1 plus u by c. And when you use a square minus b square as a plus b into a minus b in the numerator, you will get the same formula, but now plus will be in the denominator and minus sign will be in the numerator, like this. So it looks same, it is different. C plus u by c minus u. Here it is c minus u by c plus u, right? So in this case, nu is less than nu naught. Here, nu is greater than nu naught because source and observer are moving toward each other. Here, source and observer are moving away from each other. So nu is less than nu naught, right? There's another case if the radiation is observed transverse to the direction of motion. That is, theta is 90 degree, and we have nu is equal to nu naught times square root of 1 minus u square by c square. Let me encircle it and name it as equation 5. I repeat, the radiation is observed transverse to the direction of motion, theta is 90 degree, Let me check the figure. When theta is 90 degree, source is going this way, but you are receiving the radiation at right angles to the direction of motion. In that case, you have to put theta into 90 and equal to 90 degree in this formula. Cos 90 is 0. So your denominator will become 1, and you have just nu is equal to nu naught times 1 minus u square by c square under the square root, like this. Here, in this situation, nu is less than nu naught, right? Nu is here less than nu naught, as you can see. Right? This is sometimes called the transverse Doppler effect. Transverse Doppler effect. When you are receiving the radiation transverse to the direction of motion, such a situation is called transverse Doppler effect in case of light, right? So these equations for the relativistic Doppler effect 2, 3, 4, and 5 allow the change in wavelength to be obtained via lambda is equal to c over nu, because all observers measure the speed of light as c. So you can use these equations to find the change in wavelength. Lambda, relation between lambda and lambda naught, using the relation lambda equaled c by nu, right? So we'll do now some sample problems that will help you to understand how to use these equations. So let me go to the sample problem. Sample problem goes like this. It says, use black color, a distant quasar, the kind of star, is moving away from Earth at a speed u. An astronomer is searching for a certain spectral line in the light from the quasar That line emitted by atomic hydrogen is observed using hydrogen discharge tubes on Earth to have wavelength of lambda naught equal to 121.6 nanometer. The astronomer finds the hydrogen spectral line emitted by the quasar at a wavelength of 460.9 nanometer. Assuming the quasar to be moving radially away from Earth, what is its speed relative to the Earth? Before going to solution, let me check the problem. I repeat it. A distant quasar is moving away from Earth at a speed u. An astronomer is searching for a certain spectral line in the light from the quasar. That line emitted by atomic hydrogen is observed using hydrogen discharge tubes on Earth to have a wavelength of lambda naught equal to 121.6 nanometer. The astronomer finds the hydrogen spectral line emitted by the quasar at a wavelength of lambda equal 460.9 nanometer, assuming the quasar to be moving radially away from Earth. What is its speed relative to the Earth? So let us move to the solution. So we have to find U, which equation to use. Let me check. This is the case of source moving away from the observer, right? That is this case. Nu equal nu naught times C minus U by C plus U, right? So let me use it using equation 4. Because source and observer are moving away from each other, we have this relation. Using equation 4, we have, what is equation 4? Nu is equal to nu naught times square root C minus U by C plus U. C minus U over C plus U. Equation 4, this one. Now, we are given lambda naught and lambda. This is our lambda naught. This is our lambda. So we have to change this equation using the relation C is equal to lambda nu. So nu is C by lambda, and nu naught will be C by lambda naught. So making this substitution, you can write, instead of nu, you write C by lambda. Instead of nu naught, you write C by lambda naught, right? And you have this factor in the square root C minus U over C plus U. Now C will go. Then you have 1 over lambda is equal to 1 over lambda naught times this factor. So if you write, you will write directly lambda equal lambda naught. You are doing the reciprocal of the equation. When you do that, C will cancel out. This will be reciprocated. So this factor will be then square root C plus U by C minus U, right? Lambda equal to lambda naught C plus U by C minus U. You can write the same equation as, write it in the next bit or the same page. Let me move to the next page. You can write it as lambda equal to lambda naught square root 1 plus U by C over 1 minus U by C. Check it. 1 plus u by c over 1 minus u by c. Because take here LCM, it will be lambda equal to lambda naught square root c plus u by c over c minus u by c. C will go, right? That is same as square root c plus u by c minus u, which is this equation. Square root c plus u by c minus u. So you can write it this way. Lambda equal to lambda naught times square root 1 plus u by c over 1 minus u by c. So we have to solve for speed, or me use this color. U by c, I solve it. I want u. U by c is lambda by lambda naught square minus 1 over lambda by lambda naught square plus 1. You can check it. U by c is lambda by lambda naught square minus 1 over lambda by lambda naught square plus 1. Lambda over lambda naught is 460.9 nanometer over 121.6 nanometer, which is, when you calculate it, you can check it, 3.79. Lambda is 460.9 nanometer. This is lambda, 460.9 nanometer. Lambda naught is 121.6 nanometer. So when you find this ratio lambda by lambda naught, it is 3.79. So when you use it here, use another color here. This color implies u by c is equal, this ratio is now 3.79, 3.79 square minus 1 over 3.79 square plus 1. 3.79 square minus 1 over 3.79 square plus 1. And when you calculate it, you will get u by c equal 0.87, or u is equal to 0.87c. So we have found u 0.87c. What is the conclusion? Conclusion is, I'll write it here. The quasar is moving away from Earth, moving away from Earth at 87% of the speed of light. Speed of light. And remember, this calculation determines only the radial or line of sight component of the relative velocity, right? You can see from this problem that a Doppler effect causes the wavelengths of light from objects receding from Earth to be lengthened or shifted toward the red long wavelength end of the visible spectrum. Hence, it is known as the redshift. Let me write it. The Doppler effect causes the wavelengths of light from objects receding from Earth to be lengthened or shifted toward the red, that is long wavelength end of the visible spectrum. Hence, it is known as the redshift. You can see this quasar was moving away from Earth at this much speed. So lambda observed is 460.9 nanometer, but lambda naught is 121.6 nanometer. So because of its relative motion, the wavelength observed is longer, so it has lengthened the wavelength of the observed light. There is a shift in the wavelength towards red end of the visible spectrum, so it's called redshift. Now I will give you some homework. Simple problems on Doppler effect in light. Homework. Question 1. A star is receding from the Earth at a speed of 5 into 10 raised power minus 3 c. C is speed of light. What is the wavelength shift for the sodium D2 line, which has wavelength of 5890 angstrom. This is my question first. Let me check it. A star is receding from the Earth at a speed of 5 into 10 raised power minus 3c. What is the wavelength shift for the sodium D2 line with a wavelength of 5890 angstrom? Then remember, in the sample problem we just did, we had to calculate U, and wavelength shift was given, lambda and lambda naught were given. Here U is given. You have to find out the wavelength shift, that is delta lambda minus lambda naught, right? Let me go to the next question. Suppose that the Doppler shift in the sodium D2 line, the wavelength 5890 angstrom is 100 angstrom when the light is observed from a distant star. This is distant. Determine the star's velocity of recession, so it is similar to the sample problem we did. Let me check it. Suppose that the Doppler shift in the sodium D2 line, 5890 angstrom wavelength, is 100 angstrom when the light is observed from a distant star. Determine the star's velocity of recession. So this is all for today. Do your homework, go through all the video lectures, listen to these video lectures carefully, don't miss any video lecture, learn at your pace, make a copy of it, notebook of it, notes out of these video lectures, and don't forget to subscribe and like my channel. You can also comment in the comment box. Thank you. God bless you. Assalamu alaikum.